Well, I want to thank the organizers for inviting me to talk today, particularly on a topic that does not involve fermentation, so I think that was great, very brave on their part. So as we all know, for studying dietary fiber for many years, that there are considered to be two important characteristics of dietary fiber that might explain their physiological effects. One certainly is susceptibility to fermentation, and we've heard a great deal about that here at the Vahouny Dietary Fiber Conference, or what I think of as the Fiber Fermentation Fest, or F cubed for short. And I'm not going to talk about that. So I'm going to talk about the other characteristic of dietary fiber, arguably the one that was the initial focus of dietary fiber, and that was viscosity. Many years ago, the importance of viscosity was demonstrated by work by Jenkins and Gallaher, where they found that when they fed very viscous fibers, that they attenuated the blood glucose response. Subsequently, when people got interested in the cholesterol-lowering effect, though, certain people promoted the idea that the fibers, the viscous fibers, which were the ones used at that time, were almost always also fermentable, that it was the fermentation products of the dietary fiber that were responsible for the cholesterol-lowering effect. Jim Anderson, in particular, was responsible for promoting the idea that propionate was taken up from the large intestine, carried to the liver, and inhibited cholesterol synthesis, and that was what was responsible for the cholesterol-lowering effect. However, other people had studied the effect of these viscous fermentable fibers and found that, in fact, when you did that, what you found was that cholesterol synthesis in the liver increased, not decreased. So that made it a very complicated situation to understand. So many years ago, we decided to look at this and try and tease apart whether it was the viscosity that was responsible for cholesterol lowering, or was it the fermentation that was responsible for cholesterol lowering. Given that most of the fibers that we consume that are viscous are also fermentable, this did create a bit of a problem. So things like guar gum, pectin, beta-glucans, they're highly fermentable, they're highly viscous. So the approach that we used to try and tease that apart was that we would get something that was viscous but non-fermentable, and therefore we could separate the fermentation effect from the viscosity effect. And so that started my love affair with this fiber. This is hydroxypropyl methylcellulose, HPMC for short. This fiber is highly viscous, it is not fermentable, and it's also available in a wide range of viscosity grades. So you can actually feed different viscosity grades using the same amount of the material. So it is also safe to consume by humans. It is GRAS. It has been used in the food industry for many years as an emulsifying agent, but they have done trials with the quantities that you would need to feed a human and found no side effects of it that differed in any way from the control. So hydroxypropyl methylcellulose created an opportunity for us to separate the effect of fermentation from viscosity in looking at the cholesterol lowering effect. So our first foray into this area of looking at the effect of HPMC with different viscosities in an animal model, we chose to use the hamster. At the time we did these studies, the hamsters were being promoted as a good model for studying dietary effects on cholesterol for the reason that you could feed a relatively small amount of cholesterol to these animals and their plasma cholesterol would show large changes. Whereas in the rat, you have to give very large amounts of cholesterol to see changes in the plasma cholesterol. So that was a real advantage. They were also being promoted as having a bile acid profile that was more similar to humans. That was not true, but they were promoting that. But it does have a gallbladder, that is true, so that is something similar. One of the disadvantages of using hamsters, though, is that they're cute. And so getting the graduate students to kill them was not an easy thing to do, sadly. So in these, some of these early studies, we would feed diets containing either cellulose, which is non-fermentable for the most part, also obviously not viscous, and then we'd feed a range of viscosities of HPMC. In the hamsters, we did studies at variable lengths of time, but I'm going to just talk about one of them that we did where we fed for 3 weeks. So then we would fast the animals overnight, then we would meal feed them a couple grams of their respective diets, and then we would anesthetize them, take out the small intestine, and we would collect the intestinal contents. The way you do that is very low tech. You pull out the intestine like a piece of spaghetti, and you use your finger, and you simply strip out the contents. That was not something the graduate students were excited about either. So we would collect that. We had to centrifuge the contents and take the supernatants because the way we measured viscosity, the particulates in the whole contents would jam the viscositor basically and prevent its viscosity from being measured. This is a picture down here of this viscometer we use. It's called a cone plate viscometer. It gives you absolute viscosity, and you can use very small sample size because, as you can imagine from hamsters, you don't get a lot of intestinal contents. And then we measured plasma cholesterol. And the figure on the left shows the intestinal contents supernatant viscosity, which is what we actually measured, and on the y-axis it shows plasma cholesterol. And you can see that as viscosity increased, we got a decrease in plasma cholesterol, and it followed a pattern of exponential decay. That is, at low viscosities, increases resulted in large changes, and as you continue to increase viscosity, the effect declined. So if you do a very simple thing, just simply take the log of the intestinal contents viscosity, again plotted versus plasma cholesterol, you get virtually a straight line, meaning that this effect is highly predictable. The line was so straight it looked like we made up the data. But again, I want to emphasize the point in terms of viscosity. At very low viscosities, it only takes a small increase in viscosity to get a rather dramatic effect on lowering cholesterol. So that's a real positive thing because, as we all know, getting very viscous foods manufactured so that they're palatable is very, very difficult. So, as I said, we did these many years ago. And we did a lot of studies. We repeated this. Unlike David Krzyzewski's wisdom, we totally ignored that. We repeated the study many times, and it always worked. And then other people have done it. It has worked for them. It's been done multiple times in humans. HPMC always lowers cholesterol. So we then wanted to say, well, okay, that's great. So viscosity is clearly involved in lowering plasma cholesterol. There is very clear from the animal data and the human data. But HPMC is not a natural fiber. Most food companies were not interested in using that. They wanted to stick with natural fibers. And so the challenge there is almost all natural fibers are also very highly fermentable besides being viscous. So we wanted to know then, does this same phenomenon of this relationship between viscosity and cholesterol lowering also hold for fermentable but viscous fibers? So obviously a very common fermentable and viscous fiber are the beta-glucans that are so common in oats and barley. So we chose to do that, to look at that, and so we examined the cholesterol lowering effect of beta-glucans, and we chose to use rats. The reason is that hamsters have a pouch in their stomach where they ferment materials. And so if you feed a fermentable fiber, they'll ferment it partially in the stomach, thereby reducing its viscosity. And so that makes the hamster not a particularly good animal when you're studying fermentable fibers. So we went back to using the rats. And in the rat, unless you feed unrealistic amounts of cholesterol in the diet, very rarely does their plasma cholesterol show much change, and so it's better to focus on liver cholesterol in a rat, which does change very much with dietary interventions. So the first study we did, we used a beta-glucan enriched product that was a product of the Quaker Oats at the time. They referred to it as beta-trim at the time. And so we had three different versions of this, low, medium, and high beta-trim, which varied in the amount of beta-glucan concentrated in it. So we fed rats a diet containing 25% cholesterol. All the diets were balanced for macronutrients, including total dietary fiber. So the amount of beta-glucan varied, but the total amount of dietary fiber was the same. We fed them for about a month, and we also determined cholesterol absorption in these animals using what's called the fecal isotope ratio method, where you feed a radioactive plant sterol, which is a non-absorbable compound, and then you also feed a radioactive cholesterol, for example, a tritiated beta-sitosterol and a C14 labeled cholesterol. And by looking at how that ratio changes from the time you fed it to the time you collect it in the feces, you can determine cholesterol absorption. So that's what we did. So on the left hand here, we see intestinal contents, supernatant viscosity, and on the bottom, the various groups. So cellulose and the low beta-glucan groups had minimal viscosity. It increased with the middle concentration of beta-glucan and then increased significantly in the contents with the high beta-glucan concentrate. And again, just looking at the beta-glucan diets, we have on the right side the intestinal contents supernatant, and then excuse me, I confused that. On the y-axis, we have the log of the supernatant viscosity, and on the x-axis, we have the beta-glucan concentration. And the point I want to make here is that as you increase the beta-glucan concentration in the intestines, that's what's driving the increase. The reason I show this is people over the years have asked me, well, does the protein contribute to the viscosity? And the answer is no, it doesn't. It's only the beta-glucans. If you don't have a viscous fiber in there, the viscosity is close to water. So now this is the liver cholesterol concentration here on the left side of the screen. And then again, the log of the intestinal contents, supernatant viscosity, and once again, you can see the relationship is extremely linear, an R squared of almost 0.9. So as you increase the viscosity and express it as the log, you get a decrease in liver cholesterol. And then on the right, just looking at the 3 beta-glucan fed groups, you see the same relationship with cholesterol absorption. And this suggests that the primary effect of these viscous fibers is on reducing cholesterol absorption. That is the mechanism driving this. And we have shown this also with HPMC, this viscous but non-fermentable fiber. We see the same thing, that we decrease cholesterol absorption, and when you express it as a logarithm of the viscosity, it's highly, highly linear. So then we looked at another product by a different company. This one was called OatVantage. And so we fed either 5% of this beta-glucan isolate or 5% cellulose, again, using a cholesterol-containing diet of about 0.25%, balanced the diets for macronutrient content, fed them for about a month. And here we saw a very high viscosity with the OatVantage group, whereas cellulose, essentially the viscosity of water. The liver cholesterol was in fact reduced by the OatVantage group compared to the cellulose, so the beta-glucan product did work. Since there was only one level, we don't have a relationship here, but the reason I'm showing this will become clear in a minute. Here we looked again to confirm that it was the beta-glucan concentration that was driving the viscosity. We've always been challenged because if you look at this viscosity measurement, you see how variable it is? It drives us crazy. We always have this huge variability, whereas some rats fed beta-glucan concentrates, the viscosity is almost zero, and others it's off scale, we can barely measure it. And these are the same animals fed the same diets, they've been fasted for the same amount of time, and we always are perplexed why that is. Well, the reason is they have different amounts of beta-glucan in their small intestine. Now why that is maybe relates to different rates of stomach emptying, but something's driving it. The difference is the amount of beta-glucan differs over time within their small intestine. It's not the same for all the animals all the time. Also, there seems to be a difference in the beta-glucan's ability to create viscosity in the contents. On the right, we show the OatVantage, which I was just talking about, and the 3 different beta trims, the low, medium, high. And if you look at the viscosity produced per unit of beta-glucan, they're not the same. They're not the same. So the beta-glucans themselves differ in their ability to produce a viscosity in the small intestinal contents. So we looked at one more beta-glucan concentrate. Companies kept coming to us and asking us to do this, so we said okay. So this one was called Viscofiber. It was a beta-glucan extract from oats and barley. And so we had dyes containing either 5% cellulose or 3% beta-glucan from either the Viscofiber oat or Viscofiber barley. The total fiber content was the same, so the two Viscofibers had 2% cellulose added to it. Again, same model, 0.25% cholesterol. We fed for 6 weeks this time. And to our shock and maybe horror, we found something that was quite unexpected. The graph on the left shows the intestinal supernatant viscosity, and you can see the cellulose, of course, had no viscosity, but the Viscofiber barley had no viscosity. It was just almost that of water. The oat had some viscosity, but it was far, far less than what we would have expected based on the amount of beta-glucan there. And then when we looked in the intestinal contents, strangely enough, there was a lot of beta-glucan there. It wasn't because there was somehow magically the beta-glucan had disappeared. It was comparable to other studies, so something very strange was going on. We then measured the liver cholesterol, and nothing happened. There was no reduction in liver cholesterol. So without the viscosity there, the beta-glucan was there. The beta-glucan was in the intestinal contents, but it didn't produce a viscosity, and it did not lower liver cholesterol. So this was perplexing. So we tried to look at the in vitro viscosity of that just to see if there was something going on that would help us understand. So we measured it by using a technique that's, or an instrument that's very common in the food industry called an RVA for measuring in vitro viscosity. And so we looked at the viscosity of the Viscofiber oat and barley, which did not lower cholesterol, and compared it to OatVantage, which did lower cholesterol, and the in vitro viscosities were essentially the opposite of what we found in vivo. So the OatVantage had a relatively low in vitro viscosity, but it very effectively lowered liver cholesterol and had viscosity in the intestine. Here we have Viscofiber oat and barley. It had no effect on liver cholesterol, had no viscosity to speak of, and yet in vitro it had a very high viscosity. So we don't know the reason, but we can certainly tell you that you can't always trust in vitro viscosities to predict what will happen in vivo. That was the message from this. So to summarize these few studies that I've presented to you today, first of all, I would suggest that cholesterol lowering by beta-glucan is proportional to the log of its intestinal contents supernatant viscosity, that the log of viscosity is also proportional to the beta-glucan concentration in the contents, at least in most cases, and that finally the warning is in vitro viscosity does not always reflect ex vivo viscosity. So what I think we can conclude from this is that both non-fermentable and fermentable fibers show the same relationship of viscosity to cholesterol lowering. Doesn't matter whether they're fermentable or not. And to me, this suggests that at least for beta-glucan, and I think for other long-chain fermentable fibers that are also viscous, that the fermentability is not playing a role. It is the viscosity. It is entirely due to the viscosity that we're seeing the cholesterol lowering. And then finally, getting back to where we started, small increases in viscosity at the low viscosity range lead to large decreases in cholesterol concentration. So I'd like to acknowledge the people who actually did the work. First of all is Cynthia Gallaher, who's not related to me except by marriage, and she's holding my granddaughter there. Dr. Andrea Arikawa, Laura Freiburger was her maiden name when she was in my lab, and then Melanie Combs, who was an intern from France doing some work in our lab. And thank you very much for your attention.
Time for a quick question, if there is.
Hi, Nick Boschman. For the
HPMC, did you ever look at the effect of just the viscosity on the microbial community or any metabolites that they would produce? So not thinking about fermentation, but just the effect of viscosity on that community.
It's something we thought a lot about, but the answer is no. At the time we did most of the HPMC studies, that work was basically all being done by colony counting, and it was that's extraordinarily laborious if you're familiar with that. We did see something that suggested we were changing the microflora population because we saw a change in some of the enzymes responsible for metabolizing bile acids in the colon. And so one might suppose that that suggested of a difference in the population. Dr. Clearfield.
Dan, you didn't mention pH of the gut. In the small bowel of the rat, you can see up to a 2-unit difference. And you're milking the entire intestine. You're putting together a pH gradient into a single sample.
Mm-hmm.
And my understanding is that viscosity is highly pH dependent.
Yeah, that's a good point, Dave. I agree that we are doing that. I was aware that that phenomena is taking place. By the time we get it all together, of course, and we mix it up so that the pH would be uniform at that point. I don't know why we would lose the viscosity in one sample but not the others based on that. So, I mean, in 2 of our studies, that didn't seem to be, we saw this linear relationship, and then one it disappeared with. So it's an interesting idea. I tend to think there's something in the processing of this product called Viscofiber that did something to the beta-glucans. So
you had mentioned potential differences in gastric emptying. If you have that, in effect, you will have a different pH gradient, and that the net pH of one rat may not be equivalent to the net pH in the second rat.
yeah, that's an interesting idea. No, we've never looked at that. It's, unfortunately, to get enough contents to measure this, we have to take the whole contents, otherwise we just can't do it. And just anecdotally, the contents look different in the proximal half than the lower half, than the distal half. You can tell that just by looking at it when you're physically done. I've done this myself like thousands of times, and they are different contents. So I suspect that the viscosity would differ between the proximal and distal half of the small intestine as well. So, yeah, thanks for your comment, Dave.
One more question.
In my previous experience, the vitro viscosity has a lot to do with the size of the fragment in vitro viscosity. So I'm wondering, will size plays a role in the viscosity you observed? Because when you take that in through the digestive system, that will change the size.
Yeah, it's an interesting idea. The particle size of these, because they're extracts, these aren't like just milled whole oats or anything. They were all pretty fine powders, so I don't think they had a great deal of difference in terms of their particle size.
The molecular size.
Oh, are you talking about the molecular size of the beta-glucans?
Yes, the chain length.
Yeah, certainly that can change by the processing method, without a doubt. I mean, some really harsh processing techniques are known to depolymerize these beta-glucans, absolutely. That can definitely happen. In our in vitro work, we thought maybe the amount of starch present there was interfering with it, so we tried actually treating them with amylase first to see if that could change the viscosities, but that didn't have any effect. But no, you're absolutely right. That's a big concern with trying to isolate beta-glucans, is depolymerizing them.
All right, thank you.
Okay.